Good afternoon, everyone. My name is Ali Nokhodchi. I'm a professor of pharmaceutics and drug delivery at University of Sussex. My talk today is going to be on particle engineering of carriers for improved drug delivery to the lung. And I'm going to show you how we can modify carrier particles for better drug delivery to the lung. So I'm going to briefly touch on the fate of inhaled corticosteroids as an example. If you look at this slide, you will see that if you inhale such a formulation through DPI or PMDI, usually 10 up to 20% of the drug deposit in the lung. And then you can see local or systemic effect. And if you see systemic effect, you may end up with systemic side effects. The problem is above 70% of the formulation deposit on your throat, you swallow it and goes into your GI tract and followed by first pass metabolism, then you will see the drug in systemic circulations and you may end up with serious side effects. So my talk is going to show you how we can improve that percentage. So when you do any DPI formulations, we usually use particle size between 1 to 5 micrometers, ideally between 2 and 3 micrometers. When you put into the capsule formulations, what's going to happen? They get aggregated or agglomeration going to happen as a result of high surface energy they do have or high surface area. And if they aggregated, they're not a respirable size anymore. And you see that unhappy face. And what we're going to do, usually they mix it with coarse lactose, which is 63 up to 90 micron. And when you mix such a smaller drug particles with coarse lactose, and these fine drug particles have tendency to sit on the coarse lactose particles and give you a nice ordered mix. You will see that that's SCM for coarse lactose, that's for drug particle. You can see that drugs nicely sit on carrier surfaces. What is going to happen when patients inhale such a formulations? Coarse lactose can deposit on your throat. But what's going to happen for smaller drug particles as a result of air stream, and your lung can generate enough force to detach them from carrier surfaces. They can follow their way to lower respiratory tract. But that's not end of the story because there are lots of problems here. If you have stronger adhesion between drug particles, which are red dots here with a coarse carrier, which is lactose in this case, or green particle, and you get poor detachment, but you will get very good homogeneity or very good uniformity in the formulations, but you don't get good enough detachment. So, but if you reduce the adhesion between drug particles and carrier, although the detachment is going to be very easy, very good in terms of fine particle fraction, but the problem is you will get poor homogeneity or poor uniformity. You may end up with segregation of drug particles from carrier. You can see that you should think of compromising between detachment of drug particles and homogeneity or uniformity. So what we did actually, we're trying to modify carrier particles compared to drug, because if you look at any formulations, the amount of carrier is 100 times, sometimes 1,000 times higher than the concentration of drug in the formulations. So what we did, we produced different concentrations of lactose in water, 20%, 30%, and 60%. We dissolve them easily at 55 degrees. And when we add 5 milliliters per minute of this solution, lactose solution, into anti-solvent system, which is ethanol and butanol in this case, and within 5 minutes, you will get precipitation of lactose particles. And we use binary mixtures of these two anti-solvent system to tune the surface of lactose particles. You collect your lactose particles and dry them at 70 degrees for 24 hours. And what we did later on, you mix the fractions of particles how you want with drug, put into the capsule, and use one of these deposition equipment like MSLI, NGI, or ACI to do deposition studies and calculate recovered dose emitted dose, emission, impaction loss, and fine particle fractions. And this is the result of micromeritics characterization of crystallized lactose. And you will see that you can even get 100% yield when you do the crystallization. But our interest was on porosity of particles. If you look at the porosity of particles, you will see that commercial lactose produce 60% porosity between particles, whereas all crystallized lactose produce a higher porosity. We believe that having high porosity, making them easier dispersion when you spray or inhale such a formulations. And I'm going to show you more results on this. What we did, we tried to see what are the changes in surface of lactose. This is commercial lactose. You will see that it has got a smoother surface compared to a crystallized one. And this is crystallized lactose from pure ethanol, and the bottom one is from pure butanol. And you will see that how changes in concentrations of lactose in the solution can change the shape of carrier or lactose particles, and you get more elongated if you actually use 60%. If you change the solvent to from ethanol to butanol, you get entirely different particle shape. You will see that. And what message I can give you, so highly saturated concentration, smaller the particle size, and ethanol produces elongated primary fine particles, but larger than if butanol used, as these are actually fine particles. And if you use binary mixtures of these two solvents rather than pure one, you can actually tune the surface of lactose particles. And you will see that some of them can give you actually nano surfaces like this one or this one. If you magnify, these are right around maybe 500 nanometers, and we call them nano surfaces. They play a major role in detachment of particles from carrier surfaces. So the role of these binary mixtures of anti-solvent is the tuning the surface of lactose particles to optimize the formulations. What we did later on, we used particle size analysis to calculate how much of those crystallized lactose particles are less than 5 micrometer, which can be used as a fines in the formulations. And when we plot against the different concentrations of lactose used during the crystallization, we found that actually, for example, the ratio of 20 to 60 ethanol butanol gives you the highest concentrations of fine lactose. As you increase the concentration and the concentrations of fine particle lactose, or the amount of fine particle lactose going down, and you will reach around 1.5%. And so when we calculated the fine particle fraction, we noticed that the commercial lactose giving us around 20%. The drug was salbutamol sulfate in this example. If you increase the concentration to 20%, you will get around 35%, and 30% lactose give you around 35, but 60% is slightly smaller. So what is the reason having better fine particle fraction or detachment of drug from crystallized lactose? I have shown in this figure here. If you look at the commercial lactose, you have a smoother surface. So the contact area between drug and the carrier surface is much higher. That means you need high inhalation force to detach them from carrier surfaces. But when you have nano surfaces like this, which is 30% is a good example, the contact area between drug and these nano surfaces or these jagged surfaces is much smaller. So you need less inhalation force to detach them from carrier surfaces, and you will see better fine particle fraction. But if these roughness or these crevices is large enough to accommodate any drug particles, and you will get poor detachment, because this drug can be lodged into these pots and the detachment is not going to be very easy. So that's the beauty of crystallized lactose, or having nano surfaces at the surface of these crystallized lactose. So a higher surface roughness leads to lower drug lactose adhesion, then easier detachment of the drug. So what we did actually, and we plotted fine particle fractions obtained for all formulations against the amount of fine particle lactose. We correlate them very well. We can say you can predict what's going to happen. So commercial lactose gives you smaller and no fine particle lactose, and you get in poor fine particle fraction or the smallest fine particle fraction. But when you increase the amount of fine particle lactose up to 3%, you will see that you will get better results in terms of fine particle fraction, and that could be another reason. But the important thing we're trying to actually tell is that the prediction of fine particle fraction based on porosity. And you can see that simply high the porosity, better the fine particle fraction. So if you calculate the porosity of such a formulations or such carrier particles, you can predict what's going to happen for fine particle fractions. So better aerosolization performance for carrier particles with higher fines content, so higher specific surface area and higher porosity. So that simply tells you actually porosity could be a very good indicator to predict fine particle fractions. So I'm moving on the next part of my talk, which is we are trying to find alternative carrier to lactose, because lactose is the only approved excipient for DPI at the moment, although there's a pure mannitol formulations on the market, but not as a carrier, as a drug. Because of disadvantage with lactose, such as unsuitability for diabetic patients or lactose intolerant patients cannot take it. But whereas mannitol could be very good carrier for such a formulation. So we have written an editorial on this, which published a few years ago. But the problem with mannitol, commercial mannitol, is the position performance is poor. So what we're going to do, we have to modify it. So this is commercial mannitol. You will see that is roughly irregular shape. This is spread-dried mannitol, a round shape, and this is a needle-shaped particles. We use freeze-dried technique to produce elongated particles. What we did actually, in order to calculate or to measure the adhesion between drug particles and carrier, we mix the subatomic sulfate with carrier formulations, and we actually use air-jet sieve. So in air-jet sieve, we use sieve which is aperture size was 20 micrometers. As the drug particle size was less than 5 micrometers, if you apply air-jet sieve, any particles detached from carrier surfaces which is less than 5 micrometer can go through the sieve. If you pick up the sample from the top of the sieve, you measure how much drug left. You can say that which formulation actually has easy detachment. So we applied 5 seconds. We noticed that if you use freeze-dried mannitol, after 5 seconds, 47.4% of drug left on carrier surfaces. Whereas commercial mannitol, you will see 91.1% of the drug left on the carrier. That shows that freeze-dried mannitol actually much better than the commercial mannitol, because you can have easy detachment. We did it up to 3 minutes or 180 seconds. After 3 minutes, only 6.5% left on carrier surfaces, which contain freeze-dried mannitol, whereas commercial mannitol is still around 50%. You will see drug attached to carrier surfaces. That means the drug detachment is not very easy from a commercial mannitol. But using freeze-dried formulations, you can make it easier. So we did deposition studies, and we actually showed that if you use freeze-dried mannitol, you have less drug actually stick your throat. This is the throat area, which is around 10.5 micrometers. And most of the drug can enter the lung if you use freeze-dried mannitol in stage 2, 3, 4, and even filter. And when we again calculated the porosity of these crystallized mannitol and against fine particle fraction, any carrier with higher porosity, which is a freeze-dried mannitol in this example, you will get actually better deposition and fine particle fraction around 50%. And these are the values in this table. You will see that the amount of fine particle fraction is 6.8% if you use commercial mannitol, whereas freeze-dried mannitol you can go up to 47%, which is amazing, and you have a 3-time increase in the position of drug particles. And we thought if elongated carriers working very well or performing better, so let's make very, very elongated particles. That's why we did more studies. We compared commercial mannitol, commercial lactose. They are less elongated. We crystallize mannitol from water, crystallize mannitol from acetone, and we crystallize mannitol from ethanol. And ethanol give you the highest elongation ratio value. When we did actually deposition studies, and this shows actually, and the more elongated particles or carriers can deliver drug better than other formulations. And you can see that less elongated particle. You can see that this is a throat area, commercial mannitol, commercial lactose performing poorly, whereas elongated particles, they performing very well. And most of the drug can be actually find their way into the deeper airways. And what we did later on, we plotted elongation ratio value against fine particle fraction. We want to see how long we can actually increase elongation ratio to improve the delivery to the lung. You can see that an increase in elongation ratio, you can see enormous increase in fine particle fraction, but up to around 5. So beyond 5, there is no effect. So there is no point actually you make very elongated particles above 5, because of it's very difficult to make such elongated particles. Also, they are fragile. So that shows that for these type of formulations, elongation ratio up to 5 is going to give you better results in terms of performance. Why this is happening, or elongated carrier can perform better than less elongated particles? Imagine these blue dots. This is the drug particles on carrier surfaces, and this is a rectangular shape, but this is a needle shape. Imagine both of them are supposed to travel the same distance as a result of air stream. You can see that if they travel the same distance, this drug is still on the carrier surface, but this drug is out of needle shape particles. So that's why to get better performance, you need less inhalation force for needle shaped carrier, whereas you need high inhalation force to detach these carrier particles, these drug particles from carrier surfaces. That could be one of the reasons. The final part, which I'm going to talk for a couple of minutes, is the effect of the shape of fines, because so far we proved that if you have elongated carrier, they're working very well in DPI formulations. How about if you have elongated particles as fines particles in ternary formulations? So let me give you a very brief background on this. If you have lactose particles, coarse lactose, usually you have hot spots on it, and they have high surface energy. If you mix drug particle, which is the black dots, with the lactose particle, they have tendency to sit on this hot spot, and then you need high detachment force. You can see that the amount of drug detached much less, and you see this unhappy face. So what usually they do now, they usually have a coarse lactose, and they mix it with fine carrier particles, less than 10 micrometers, because these fines can sit on these hot spots and cover those hot spots. Now you can mix drug with these mixtures of coarse lactose and fine lactose. Although the drugs can sit on this hot spot, but the hot spots are much smaller than actually on these smaller particles compared to big coarse lactose. So that means the detachment is going to be much easier. What we did, we look at the effect of these shape of these fines, what's going to happen. And we crystallized, or we obtained spherical mannitol, which is less than 10 micrometers. We got rectangular shape of mannitol, less than 10 micron, and also elongated mannitol. When actually when you do not have any fines in the mixtures of mannitol and drug, your drug can actually hold by crevices, and also your fine carrier also can go there, but you can see that you will get a poor detachment because these crevices can hold your drug particles. If you use any fines and or rectangular shape, they cannot cover these crevices. Still, you can see that although some of commercial money fines can sit on these, but still you get a majority of drug sticking into the crevices, and the detachment is going to be very poor. But if you use a needle shape as fines, you can see that how nicely they can cover these crevices. So the drug cannot actually go into these crevices or hold by these crevices or these pots, and they can sit on these fines, and detachment is going to be much easier, and you get very good detachment of the drug. So when we did the position studies, we noticed that actually when you have a needle shape fines particles, they're performing better. You can see that in stage 1 of MSLI, less drug deposited, whereas more drug deposition happen in other stages, which is the area for deeper airways for drug delivery to the lung. And that takes me to the conclusion. And so we prove that nanosurfaces are very important in pulmonary drug delivery of drug to the lung. And crystallization of carrier particles from binary solvent is a good approach to optimize the carrier properties for DPI formulations. The shape of fines is extremely important, so we need to pay more attention towards these if we are using ternary formulations. And also mannitol could be the best alternative as carrier in DPI formulation. And finally, thanks very much for your attention.